attached to a string and immersed in a tank of water. All right, what's the volume? How do we use those two numbers to get volume?
Density
times mass.
Right. I'm going to take 27 kilograms divided by 2.7 kilograms per meter cubed, and I get meters cubed. Right? You make the units work. Okay? So that's the first thing we get. My volume within there. So 0.01 meters cubed. Determine the tension in the string when it's completely immersed. Well, if it's outside the water, doesn't the string have to hold the entire weight? So that's going to be 27 times 9.8. If it's in the water, tension doesn't have to hold all of it, because the water's going to hold some. Right? Now, does aluminum float in water? Solid aluminum. No. Density of water is 1,000. Density of aluminum is 2,700. Definitely sinks. All right? But what's the buoyant force? Well, the volume of the aluminum cube was 0.01. Won't that be the volume of water displaced? Okay? So the volume of the water, what's the weight of the water displaced? Well, I'm going to do 0.01. That's my volume. Right? Times the density, 1,000. Times G, 9.8. All right? You get a buoyant force. So 1,000, 110, 98. Right? I have a buoyant force of 98. If it was out of if the aluminum was out of the water, what's 27 times 9.8? What is it? 264.6. Okay, 265. Right? So out of the water, the string has to hold 265 newtons. In the water, has to hold what?
98.
98 less than that. Right? Because the buoyant force is worth 98 newtons. So let's see what they do. Force of tension plus force buoyant. Come on. All right. What they're doing here, they're doing some of the forces. When you're holding it and it's just submerged in the water, is it accelerating? No. That means the sum of the forces equals 0. All right? And we'll do more of these in class for this next 6 weeks. All right. So the force buoyant, density times volume times gravity. That's where we got our 98 newtons. Force of tension is going to be gravity, force of gravity of the aluminum minus force buoyant. So 27 times 9.8 minus 98, 166.6, 167. All right, we're not going to do all of this. I want to get to that. Bermudas. Right. You can look through on this one again because you have that one. Ice floats because the density of ice is less than the density of water. All right, fluids in motion. We will again assume ideal situations. All right, which means that the fluid's going in straight lines. You've all seen commercials, like for car commercials, where they have streams of the gas, the wind's being blown across the car, and they have streams of smoke. Okay, and they stay in the nice stream. That's the streamline flow. All right, they never really show you the back of the car, because at the back of the car it goes and gets all messy. All right, when it gets all messy, that means your gas mileage goes down. If you can have laminar flow, smooth flow over the entire car, you have great gas mileage. All right. Have anybody noticed at the back of trucks, they now have something that they're adding to the back of 18-wheelers that are doing long haul distances? They actually have doors that open up. All right. It decreases the boxiness of the back of the truck and makes the air flow over and around the truck better, which means they're getting better gas mileage. And it's something like a 15% increase. That's pretty substantial. Okay? But if you look at the back, it's not just this box anymore. They have this thing that opens up. I saw that and was like, hey, really cool. Why didn't I think of that? But I didn't, not in the time. All right, so if I have laminar flow, this is called laminar flow. I can change the distances nice and smooth. When I put an object into it, it splits it, and what happens is you have this turbulence in the background. If I can get rid of this turbulence in the background, and you do that by making this into a wing back here, right? It's why when you look at an airplane wing, it can be short and stubby on the front side, but what's the back side look like? Long, smooth, goes out to a point. So that I get the air to laminar flow over the wing. That allows better. All right, consider flow rate. Let me ask you this. How many of you ever had to like water a garden? Okay, and all you have is the hose. You don't have one of those nice nozzles that you get to do all the changes with, right? What do? Put your thumb on it. What happens when you put your thumb on it? The water. Why does the water go farther? Because it's moving faster. The volume per time, how much water is leaving your house, is the same amount of water that's going past your thumb. If I don't have my thumb over it, I have a big area, right? And I just get this little amount of water. I mean, it looks like a little amount, but it's still the same amount of water. If I close off most of that, I still need the same amount of water to go. But to do that, the water has to go a lot faster. That make sense? Okay, now, that totally makes sense, and that's exactly what happens. To get the same amount of water to flow, when I close off the cross-sectional area, I need what's left to go faster. And because it goes faster, it goes farther. We good, yes? Okay, so you have 4 lanes of traffic. They're going to go down to 2 lanes of traffic. What happens?
Slows down.
You slow down. Do you not understand how stupid that is? If I go from 4 lanes of traffic down to 2, I need my 2 lanes of traffic to go faster. Or what happens? You get a traffic jam. And it's automatic. Y'all slow down. I don't. I really do try to get everybody to go faster. Because it's physics. If you go faster, everybody gets through in the same amount of time. But no. I look at the world a little differently, right? It's just not as that. So, volume. What's volume going to be? It's going to be the cross-sectional area times some distance. If I take that distance divided by time, what is meters per second?
Velocity.
Velocity. So think about it. I have cross-sectional area times distance over time. That's cross-sectional area times velocity. That's a flow rate. And the flow rate that's happening here in this big one has to equal the flow rate that's happening here. Which means A1 times V1 has to equal A2 times V2. This is also a rule of conservation of mass. Because the amount of mass per time has to be the same. Right? And that's the density. We do all of that. We do that. H over T, that's a velocity. Right? And if it's one constant fluid, don't my rows cancel because it's the same stuff? And we get A1 V1 equals A2 V2. All right? This is the equation of continuity. I think it's a really logical equation and one that hope really truly makes sense to you. This is, I'm not going to worry about it. It's a dimensional analysis problem. All right, Bernoulli's equation. You haven't seen part of these things. I'm gonna rewrite this. Clean the board here for a second.